Thanks. The C Prime Talk Series is a talk series that happens about every other week, and it aims to accomplish these goals. So its purpose is to showcase physics-related research to the physics community in an accessible way. We hope to foster an inclusive community in the physics department through interaction and discussion questions throughout the talk. We try to feature speakers with a wide variety of backgrounds, experiences, and research focuses. We highlight unique paths people take to becoming physicists. Hopefully non-linear ones is the ones that we're trying to highlight. And we hope to provide students with experience in presenting research, communicating science in a way that's jargon-free. Yeah, so today we have Trevor giving a talk. We're very excited to have Trevor. If you have a question throughout the talk, please use one of the Zoom features that either like raise your hand or clap or something, and we'll call on you. So otherwise, keep your microphone muted so the speaker can talk. Okay, here we go. Good luck, Trevor.
Thank you. Yeah, so my name's Trevor. I'm a third-year graduate student here at Colorado, and I want to tell you about, I guess, the title of my talk, which is What's the Matter with the Universe? So in my talk, hopefully I'll convince you there's a problem and that my kind of research is maybe on track to solve it. So before I get started with the research part, I want to tell you a bit about myself. I grew up in Kansas City, which I'm showing you in a picture here. Kansas City is in Missouri. It's about a 9-hour drive east of here. And Kansas City is mostly known for two different things. The first, which is might be my favorite, is the barbecue. There's very good barbecue there. I miss it when I'm not at home. And the other thing is that it has two sports teams that have been mediocre for most of my life, but in the last 5 years or so have been vastly outperforming how they've been doing. It's been a lot of fun for me. The Chiefs just beat the Broncos, which I enjoyed a lot, at least. A bit about myself. In high school, my main extracurricular activity was debate, which sort of looks something like this, didn't have much to do with science at all. And I also like playing soccer. I don't think I was ever quite this athletic, but I did play goalie. Do play goalie, hopefully still when COVID will allow me. So this is sort of what I did outside of school. Inside school, I was always at least somewhat particularly interested in science. I took, AP Bio, AP Chem, AP Physics, and I liked the idea of science. I thought I was learning something cool about the world, but I definitely didn't have any, concrete ideas of what science research was, certainly, or what, a career in science would be like, or even majoring in it. But from high school, I knew I was particularly interested in chemistry and physics. So when I went to college, I figured I would want to major in one of those two areas. Here's where I went to college. This is a picture of Amherst College. It's a small liberal arts school in Western Massachusetts, and it's very different from Boulder. It's less than 2,000 students, and they're all undergrads. And there are some pros and cons to that. At least academically, some of the pros are that you get a bunch of really small classes where you get to know the professors. I ended up double majoring in physics and philosophy, and my classes for the majors were around 10 students on average. So that was really nice. And on the research science sides of things, it's actually pretty easy to get involved in a lab because there are no grad students. All the professors know that. They need undergrads to start working in their lab. So it's pretty easy to get involved in research. And obviously, as you can see, it's very pretty to be in the Northeast in the fall. You should go if you have a chance at some point, maybe in a year or so. The cons, however, to going to a school like Amherst are that there's, it's a small school with only undergrads. There's significantly less research going on there and less funding for the research that is there. So that's one of the drawbacks. Another drawback, which I didn't really appreciate till later on as an undergrad, when I was considering applying to grad school, I didn't really know any grad students because there weren't any around on campus. So I couldn't ask them about the application process. Even going in, when I was starting to consider grad school, why would you want to go spend 5 or 6 years after you graduate undergrad doing school again, not getting paid very much? Didn't really have anyone to talk to you about that. So I would encourage you, if you're at all curious about going to grad school or think that's something you might want to do, take advantage of being at a place like CU with plenty of grad students around. There are plenty of us that will be happy to talk to you about why we chose to come to grad school and help you try to figure out if that's the right step for you. So that's where I went to college. Like I said, I was interested in chemistry and physics. In my first semester, I took a chemistry class that I didn't like very much. So in my next semester, I took a physics class, and it was from a professor named David Hall, this guy here. After like the first or second day of class, I walked up to David Hall and said, "Hey, I'm a freshman. I don't, know much physics. This is my first class, but I'd like to join your lab." And he's a nice guy. He let me work in his research lab. But it honestly wasn't the best research experience. I didn't have too much structure. I had a project that I was told to work on my own, but I didn't have any like times I had to come into lab. I was a freshman. There were plenty of other things I'd rather be doing. So I didn't end up doing too much work in his lab. And then on accident, I plagiarized on a lab report for his class. Don't do that. Don't plagiarize on a test or a lab report or anything like that. That's a bad idea. But long story short, my research experience with David Hall didn't work out. So later on, by my sophomore year, I knew that I wanted to apply to research opportunities over the next summer. But my problem is I'd only ever taken 2 physics classes, and they were both with David Hall. And I needed 2 letters of rec to apply for these research opportunities. So I went up to another professor, a guy here named Dave Haneke, and I asked if I could work in his lab over the winter break of my sophomore year. But the way I did it is I went up to him and I said, "Hey, can I work in your lab this winter so I can get a letter of recommendation?" And when you go up and you want somebody to write you a letter of rec, that's not how you lead. You don't say, "Hey, can I do this for you so you can do something for me back like a month later?" It's okay to want to get a letter of rec from somebody, but that's really not the best way to lead into that. So perhaps unsurprisingly, since these are the 2 guys that wrote my letters of recommendation, when I applied to research opportunities around the country over the summer, I did not get any. But I also, in addition to applying to REUs, whatever they're called, I forget what it stands for, around the country, I also applied to work at Amherst College itself doing physics research there. And the way that works is you apply to the department, and the department sort of assigns you to a professor. And maybe not very surprisingly, I was assigned to work for a different professor. This is a guy named Larry Hunter. And my research experience with Larry went a lot better. I worked with him for about 2 years, pretty much all of my junior and senior year. And I really enjoyed the research I was doing with him. And that's actually, it's the exact same stuff that I'm still doing here that I'll tell you about later in the talk. So that, was a bit of a bumpy journey, but I think turned out pretty well. But after I, as a senior, I decided I wanted to go to grad school. And I ended up going to grad school to work for one of Larry Hunter's friends, a guy named Dave DeMille here. And I was a graduate student at the University of Yale. And I was there planning to get my PhD there. Before I get into that, here's a nice picture of Yale. This is actually a very pretty forestry building. And behind it, you see a much sadder looking physics building. And I worked in the basement of that physics building. That's normally how it goes with physics buildings on campuses around the country. So I was at Yale. I was there to do a PhD with Dave DeMille. And I got about 2 years in until this last summer when Dave decided that he wanted to move to the University of Chicago. And I'm not a huge fan of cities. New Haven was the biggest city I applied to originally. So instead of moving to Chicago, I decided to email professors around the country saying, "Hey, can I come transfer and work in your lab?" And I don't know if any of you are transfer students or thought about transferring, but transferring as an undergrad is a very structured, formal process. There's application thing. It's a thing that enough people do that it's there's a lot of structure to it, and there's a very clear path forward. As a grad student, there's no such thing. So I couldn't just formally apply as a transfer student. I had to basically just email people around the country and ask for a job. Unfortunately, one of the guys that offered me a job is a guy named Eric Cornell. He's a professor here. And I'm working in a lab that's sort of co-run by Eric Cornell and June Yi. So I moved here this summer, and I've been here for like 3 or 4 months now as a third-year grad student. And I'm going to tell you about the work that I did here for the rest of the talk. My lab is here in Gilla, one of the buildings on campus, and my lab is actually right there. You can see it from the main quad. So that's a bit about me. So I think this is a good spot to join a discussion group or break off into discussion groups. So please introduce yourselves, turn your camera on if you haven't, and you can. And if you've joined a research group, talk about how that happened, if it was a straightforward process or not. If you haven't joined a research group, either because you don't want to or you haven't yet, you can talk about why you chose to come to Boulder, aside from the very obvious reasons I'm showing you here.
I've just pasted the discussion question in the chat. So remember, if you have a camera and a microphone, now is the time to use it to talk to your new friends. Okay, see you all in a bit. Trevor, do you want to take it back over?
Yeah, and you all can see my slides still?
Yep.
Again? Awesome. All right, so in the next part of the talk, I want to explain to you why the research I've been doing first at Amherst, then Yale, and now here is interesting. And to do that, I want to tell you a story, basically. It involves explosions, a mystery. It includes you personally, and if I do it right, you'll understand why I think what I'm doing is cool. So let's see how successful I am, I guess, if I can change the slide. All right, so once upon a time, there was an explosion. It looks sort of like that, but that was a pretty small explosion. So we're gonna try that again. Once upon a time, there was a really big explosion, like something like that. In fact, it was such a big explosion that billions of years later, it came to be known as the Big Bang. And after the Big Bang, lots of things have happened. Stars were formed, galaxies were made, Earth was made, we're here. But one of the important ones, at least for the context of this talk, is that there was a guy named Albert Einstein who came along, and he came up with this equation. And I expect, regardless of how much physics you have or haven't taken, this is an equation that just about everybody knows. So we have energy is equal to mass times the speed of light squared. And what this equation really says is that energy can turn into mass, and mass can turn into energy. And how much energy turns into but if you have this a certain amount of energy, it'll turn into a given amount of mass given by the speed of light squared, which is just a proportionality constant. So it tells you if you have this much energy, you get this much mass, and vice versa. This is actually exactly what happened after the Big Bang. The Big Bang was a huge flash of energy. It happened at a point. And this red arrow is supposed to be the direction of time. So as you go farther this way, time goes on. There was a big flash of energy somewhere here. And over here on this side, we have a whole bunch of mass. And so far, you might be thinking, well, this makes sense. The equation says energy can turn into mass, and I see a picture of energy turning into mass. But I told you there's a mystery. So what's the mystery? And the first mystery that we can see here is that if we look at this equation is way out of balance. Astronomers, astrophysicists have looked up in the sky and they can see how much mass there is currently in the universe now and how much energy there was at the Big Bang. There are ways to tell that too. And if you look at this equation, there's way more energy than we see in mass in the sky, according to E equals mc squared. So something funny is going on here. We don't. It's not obvious yet quite what's going on. So to understand this sort of mystery, let's take a more careful look at this equation, E equals mc squared. Now, I told you that energy can turn into mass, and that's true. But if we look more carefully, we see that when energy turns into mass, it turns both into matter and into antimatter. And I want you to think of matter and antimatter as twins. One that I'm showing here wearing a red shirt, and another that I'm showing here wearing a blue shirt. And I'll get into why you should think of them as twins a bit later on. But basically, this is already confusing, right? Because on the last slide, I showed you that energy turned into a whole universe made of all sorts of stuff, like planets, stars, and galaxies. And it's all made of matter. All of the mass we see out in the universe now is made of matter. And there's no antimatter to be found. So what's going on here? If energy can turn into matter and antimatter, why is our universe only full of one of these twins? Why is it only full of the red twin matter? And to help answer this question, we're going to have to take a more careful look at what matter and antimatter are. So let's first start with matter. I guess just before I tell you about matter, I want to show you this diagram. And this diagram is a diagram of 17 particles. These 17 particles are the 17 fundamental particles in the universe. They're all predicted by one super complicated fancy equation called the Standard Model, which is our equation that tells us how all these particles interact. It predicts these 17 particles, and we've gone out and we've looked for as many particles as we can find. And so far, we've only found these 17 particles. So these are the 17 fundamental particles that make up everything else in our universe. They may seem pretty unfamiliar. There are some weird ones in here. There's a particle called a charm quark and a strange quark. And if you have no idea what those are, that's okay. I don't really know what most of them are either. But there are 4 here that are my favorites that I want to tell you a little bit more about. In the top left, we have 2 different kinds of quarks, an up quark and a down quark. And you may have never heard of these quarks before, but you've almost certainly heard of particles that are made out of these quarks. So if you take 2 up quarks and you combine it with a down quark, you get a proton. If you take 1 up quark and combine it with 2 down quarks, you get a neutron. And protons and neutrons together make up a nuclei of all the atoms in the universe. Now, if we look down here at my favorite particle, which is an electron, electrons orbit around nuclei and they make atoms. So up and down quarks make protons and neutrons in different ratios. Protons and neutrons together with electrons make atoms. Atoms together with other atoms make molecules, and that's what makes up all the stuff, you know, that makes up us, that makes up the rooms we're sitting in, you know, the whole planet Earth, galaxies, whatever. So these are the 3 main particles that make up all the stuff around us. And there's one other particle I've highlighted here, which is a photon. Photons are just the particles of light. Yeah, it's just the light we see coming out, you know, that lets us, you know, see all the stuff around us and lets you see my talk. And together, these 4 particles, if you take up quarks, down quarks, and electrons, you can make atoms and molecules. Atoms and molecules interacting with light is exactly what my field of physics studies called AMO, or atomic, molecular, and optical physics. So that entertains a whole bunch of physicists. And also these 4 particles together make up all of chemistry and all of biology. And really, you can go a very long way with just these 4 particles. So these are really the only 4 we're going to need to focus on. But I'll simplify it even a bit more. If we just look at these 12 particles here, these are the 12 particles that make up matter. These, you know, make up all the physical stuff that we can like pick up and touch and see. And this is it. And almost all of them are these 3 particles here. So this is what matter is. This is the twin that wears the red shirt. So what about antimatter? What about the twin that wears the blue shirt? So here on the left side of this diagram, these 12 particles that I've underlined in red, these are the matter particles, the particles I've already told you about. What the new ones here are antimatter are the ones underlined in blue. And you notice that there are also 12 particles, and almost all of them have very similar names to one of the particles over here, which is why I call them the antimatter, like a twin to matter. Because for every particle of matter, there's an associated antiparticle, which you could think of it as its twin. Yeah, so if we take a more careful look at one of these twins, I said the electron was my favorite particle. We're all pretty familiar with the electron. The electron has a mass that we've measured. We know that it has -1, or it's negatively charged. And it has a property here called spin, which I'll talk to you a bit more about later in the talk. But electrons are particles that we have here. We know all of its properties. And there's the twin particle to electrons called the positron. And the antimatter twin of any particle is going to have the exact same features of the original particle, except it's going to have the opposite sign charge. So the positron here has +1 charge. And then if we look here at the up quark versus the anti-up quark, you'll notice that all of its properties are exactly the same, except the charge is flipped. So each of these particles have an antiparticle twin. It's just like the particle, except it has the opposite charge. And as you know, pretty much everything around us is made of matter. The standard model is the theory that predicts, that sort of explains how these particles interact with each other. And it explains really well how matter interacts with each other. And we test these explanations all the time just by seeing how particles interact with each other. And the standard model says that these antiparticles, when they interact with just themselves, they're going to interact the exact same way. So basically, you could take my entire room, including myself, made of all sorts of stuff made of matter, replace it with the twin antiparticle partners, or the antiparticle partners, those particles, and you'd get the exact same room. All the same stuff would be happening. Things would have the opposite charge, but that's, the same kinds of particles would repel each other. The same kind of particles would attract each other. You basically get the exact same thing over here. And so according to the standard model, according to our theory, again, these two are very symmetric. There's hardly any difference. It's nearly impossible to tell a system made of matter apart from a system made of antimatter. And so this symmetry, according to the standard model, this symmetry, according to our theory of explaining what's going on, is going to be very important later on in the talk. So just remember, these twins are basically the exact same thing. They can do all the same things as each other. They just wear different colored shirts, basically. Okay, so there's one more thing that you all should know about antimatter. And that's sort of explained on this slide. Like I showed you before, energy can turn into mass, which I'm showing you here. But I promised earlier that mass can turn back into energy. And the way it does that is when matter and antimatter get too close, they annihilate and turn back into energy. So if you take an electron and its antimatter twin, a positron, and they get too close, they'll both sort of vaporize into pure energy, and they'll both go away. So hopefully that'll make sense. But if you think about this too carefully, you'll see another problem with the Big Bang and us having a universe full of matter. According to this theory, then, basically the Big Bang happened originally. It created a whole bunch of there was a whole bunch of energy that created a whole lot of mass. That mass, according to the standard model, was just as much matter as it was antimatter, because according to the standard model, according to our current understanding of physics, there should be just as much matter as antimatter made by that process. But in the 13.7 billion of years since the Big Bang, those oppositely charged particles attract each other. Those particles should have all ran into each other and turned back into pure energy. So according to this picture, the universe shouldn't have any matter or antimatter in it. The Big Bang should have created matter and antimatter that all collided and disappeared and turned back into energy. So the standard model, the big problem with the standard model is that the big problem with the universe is that the standard model predicts an empty universe. But clearly we see a universe that looks more like this. There's way, way, way more matter in the universe than there is antimatter. And this is what we don't understand with the universe. How, if our understanding of physics is right, that treats matter and antimatter equally, how do we end up with a universe full of matter with no antimatter to be found? And that's what we don't understand. So I'm going to take a break here for a discussion.
Actually, Trevor, just before we go into the discussion question, it seems like we have a question in the audience. Lachlan, do you want to ask your question?
Okay, so you mentioned that matter and antimatter are identical other than having opposite charge. Is there a particular reason why that's the case? What's so fundamental about charge so that that's the only property that changes between them and everything else is identical?
That's a good question. I think, I'm not sure. I know that this is experimentally what we see when we can actually make matter and antimatter in a lab and look at the properties of it really carefully. And we see that it behaves the same way. It has, the same properties we can measure, but it just has the opposite charge. I'm not sure if there's a reason it has to be that way. So I guess I don't know the answer to that. It just happens to be what we see. I saw someone else raise their hand.
Yeah, Hassan.
Yeah, my question is similar to Lachlan's. So if that charge is the only thing that differentiates between matter and antimatter, what is the difference, for example, between a positron and a proton if the only difference is charge? Yes,
that's a good question. An electron is negatively charged, so the positron will have all the same properties as the electron, except it'll be positively charged. A proton is made out of 2 up quarks and 1 down quark. So if you look really carefully here, a proton, an up quark has positive 2/3 charge. 2 times 2/3 is 4/3, and then you add that to negative 1/3 of a down quark, and you also get a positive charge. But the difference between a proton and a positron is that a proton's made up of 2 up quarks and a down quark. So a proton's a composite particle. It's built out of smaller particles. And also, if you look at the masses of an up quark and a down quark, 2 times the mass of an up quark plus 1 times the mass of a down quark is much bigger than the mass of a positron. So the masses are noticeably very different. And if you look inside of a proton or a neutron, actually what you'll see other particles like floating around in there that mediate the interactions. And it's actually not something I understand super well, but there's a lot more going on with a proton because it's a composite particle made up of other particles instead of just a positron, which is a single, smaller fundamental particle.
Awesome. We can take one more question before the discussion question. Shannon, do you want to?
So with the neutrinos, it seems like they're like anti counterparts, I guess, since they don't, at least the chart says they don't have any charge. So is there any way at all to tell the difference between them and the normal ones, I guess?
So this is actually a very good question. It's one I can say a little bit more about. I don't study neutrinos myself. You'd be much better off talking to someone who does. But there's actually a big open question in physics. Like you said, neutrinos have zero charge, and their antineutrinos also, 0 times -1 is still 0. And it's possible that the antiparticle of a neutrino is itself. It's possible that there really aren't, these 3 other particles. It's really just every neutrino is its own antiparticle. And that would be really cool if it's true. We don't know if it's true. If it is true, that would tell us that our standard model, which says there really are opposite particles here, is wrong, I believe. And really, if I say anything more about it, I'll be speculating because I don't know a whole lot about this. But you're right. They're the only ones here that don't have charge. So it's possible that these antiparticles are really just the particles themselves. That's a really good point.
Thank you.
So I hope that all made sense, and you're all at least somewhat familiar with what antimatter particles are. And now I think it's good if we go on to the discussion. So the discussion's a question actually about what I've talked about. I told you that energy turns into matter and antimatter. Matter and antimatter turns back into energy. And they can go both ways, right? I could have just drawn this as just this part and this part here with an arrow pointing back and forth. So my question is, why after the Big Bang, when there was a big flash of energy, why didn't this loop keep repeating? Why didn't it look like a sine wave? You have a lot of energy some days, you have a lot of matter and antimatter some other days. Why did it, why according to the standard model and what I've explained to you so far, should this convert back into energy and then you don't really get any matter and antimatter after that? And some hints to help you answer that. When matter and antimatter annihilate and turn back into energy, they turn into light, flashes of photons, flashes of light. And if you think about that and you think about the conservation of momentum, I think you might be able to come up with a reason why this doesn't loop back and forth infinitely. So yeah, that's the break.
I think I want to ask Trevor a question. Was the implication that at Big Bang time 0, there is only energy, or is it postulated that there was matter at the same time?
At time equals 0, there is a big flash of energy, and that's it. Sorry, I should have made that clear.
I think you did, but the question then comes up, why the world did that energy, did the energy convert entirely to balanced matter and antimatter, or did it create more matter than antimatter at the start, or moments after the start? Do we know?
So that's the next part of my talk. I'll tell you soon that we think it made more matter than antimatter. But according to the standard model, according to our best theory of physics right now, which is far and away the best theory people have ever come up with, it makes incredibly accurate predictions that have been tested and verified for decades now. According to that theory, the Big Bang should have made just as much matter as antimatter. And that's really the puzzle, right? If it made just as much matter as antimatter, how the hell did we get here?
Federico?
Yeah, my question is, just like there is matter and antimatter, there is energy and anti-energy, right?
No.
No?
That is not true. You may have heard of dark energy.
Oh.
Dark energy is something different that I don't know a whole lot about, but it's really just energy that we can't explain.
Okay, so there is one general energy, and it doesn't have an anti like matter does.
Yes, it's just energy can turn into matter and antimatter. Antimatter and matter can turn into energy.
Okay. All right.
Okay, last one, Michael.
Yeah, I guess our group came to the consensus that the byproducts of the annihilation would most likely carry momentum, as well as that's in the form of the energy that's exposed or expelled from the annihilation. So, and therefore it couldn't like cause a chain reaction to just do, annihilation energy back to annihilation of, and then that energy creates more, antimatter and matter and whatnot. But just like, yeah, the byproducts would carry momentum that would take some of that energy with it, just so it wouldn't, the energy itself wouldn't like create more.
That's pretty close. Yeah. So if I guess I can just go over the answer now. Basically what happens are if you have a proton and a positron and an electron that collide with each other, you can think about them as moving towards each other with just as much velocity. And since they have the same mass, that means they have just as much momentum, which means if you look at the total momentum of the system, the energy is going to be zero, right? Then if you have zero momentum to start, there has to be zero momentum at the end. And what I realized in my group is what I maybe should have said is that the energy turns into light. Light actually can carry a very small amount of momentum per photon, even though its mass is zero. Don't want to get into why that's the case now. But basically, because the light has some momentum and there has to be a conservation of momentum, the light has to go out in opposite directions from each other because there has to be zero net momentum at the end. So for every light particle going this way, there has to be one going this way. And basically, if the light particles are flying away from each other, they obviously fly away from each other at the speed of light, and they're flying out into space. And space is a really big place. So basically, if you have a positron and electron that get close to each other, and they'll be attracted to each other because they have opposite charges, so they're likely to collide with each other, the light's going to dissipate out into space, and light doesn't really interact with light. There's no reason for the light to ever bunch up in one place ever again. So the light's just going to go out into the universe and dissipate, and there will be this very dilute energy throughout the universe, but not enough in one place to make matter and antimatter again. So that's why you start with the Big Bang, a big thing of energy. It creates matter and antimatter, and then it just turns into energy that's diluted and goes throughout the universe, but never turns back into matter and antimatter. Ian, so I have 2 sections left that I'm definitely not going to get to in 10 minutes. I can do the next one because that sort of wraps up this story. And then I guess we could end there if we want to. If people want to stick around and hear me talk about how we actually make the measurement, or like what I actually do in my lab, they can do that if they want. Would that work?
Yeah, that sounds great.
Okay. Yeah. So great discussion questions. I'm glad that you're asking questions and can to help understand what I'm talking about. It is going to make me run a little bit over, so sorry about that. Okay, so I've explained to you why this is a one-way street, and in the next part of my talk, I want to talk about the resolution to this problem, and it'll focus on the symmetry or lack of symmetry between matter and antimatter that we think is really in the universe, and one other symmetry that's very closely related to this, the matter and antimatter symmetry. So here's the situation we have. Like I said before, energy turns into matter and antimatter. Matter and antimatter will eventually recollide and turn into energy that's just light that's diluted throughout the universe. And we get a universe that looks like this. So this is what the standard model predicts the universe should look like. Now, like I said in the question session, the standard model is the most accurate theory of human history. It's really good. Every time we test it, it seems to be right. But obviously, this has to be wrong. The universe doesn't look like this. It looks something more like this, right? Planets, stars, and galaxies. So how could we possibly explain this? And what we think what actually happened, which at least someone in my group hinted at, is that we think when energy turns into mass, according to Einstein's equation here, it really makes a little bit more matter than it does antimatter, which I've exaggerated in this image. But if energy makes more matter than antimatter, then after the Big Bang, all the antimatter particles will find some matter particles to combine with and turn into energy, but there will be some matter left over. And it'll just be a little bit of matter left over, and that matter is going to fill up the universe. And that's the matter that we see in our universe, the planets, stars, and galaxies. So basically, if there's just this tiny asymmetry between matter and antimatter, if energy makes more matter, then we can explain everything we've seen so far. And this also actually answers the original question that I posed at the beginning. Remember, I said that when we look out in the sky, we see way more energy than we see mass. And this explains it, right? Because we're comparing this much energy, the whole Big Bang of energy, to just the little bit of matter that's left over, the mass of the matter that's left over. So that not only explains how we can get a universe full of matter and no antimatter, it also explains this discrepancy we see in Einstein's equation. So we think Einstein's equation is really right. If we do the calculation with this in mind, it works out. Right, but so sort of in order for energy to make more matter than antimatter, two main things have to happen. The first is that the standard model has to be wrong, because the standard model treats matter and antimatter symmetrically. It treats them the same way, and clearly energy makes more, if energy makes more matter than antimatter, they're not perfectly symmetric. So the standard model has to be wrong. And the second thing that we know, if this is what happened, is that there was a theorist, a Russian theorist named Sakharov in the 1960s, who came along and said that the only way there can be this asymmetry in the universe, for the universe to make more matter than antimatter, is that there also has to be another symmetry in the universe that we thought was a very good symmetry that would always be conserved, that's also broken. And that symmetry that has to be violated is called time reversal symmetry. So the natural question here is, what is time reversal symmetry? And I found this image with a bunch of clocks and a question mark that I like, so I'm showing that now. So the next part of my talk is to try to explain to you what time reversal symmetry is, what it means for it to be broken, and how we're going to look for it. So the way to think about time reversal symmetry is to take a video of any physical system. So the one I'm showing you here is a mass oscillating on a spring. This is a system that comes up in a first semester physics class frequently. It's described by something called Hooke's law, which just says the mass is going to oscillate back and forth, sort of like you'd expect. And this is what happens if you have a mass oscillating. Now I can pause this video here, and next I'm going to play it backwards. So here's the exact same video, just played backwards here. Ooh, there we go. It stopped for a second. Anyway, the video is playing backwards. It's fine now. Yeah, and it's clear that this is this looks like the same physical system, right? You have the same mass oscillating. It's oscillating at the same frequency. It's behaving the same way. It's following the same physical laws. So we would say this physical system respects time reversal symmetry. Now, if I stop it here, so time reversal symmetry is a good symmetry of nature when you look at a system and you play it forwards and backwards in time, and it behaves the same way. And if you just look at a video going forwards and backwards, you can see if the physical system sort of looks the same before and after. And this one looks the same, so we would say that it's behaving the same way forwards and backwards. It's a time reversal symmetric system. I got lost in my notes. Here we go. Okay, so we think that basically what Sakharov said is, in order for there to be more matter than antimatter in the universe, there have to be physical systems that behave differently when they go forwards and backwards in time. So that's actually exactly what my experiment's looking for. And we're going to look for it in an electron. I told you electrons are my favorite particle. Here is a bad drawing of an electron. Electrons are spheres, which I'm drawing as a circle here. We know electrons are negatively charged. I've drawn some negative charges. I was too lazy to fill the whole thing with a bunch of minus signs. But you can think of this as a negatively smeared charge evenly all around this circle. So that's what an electron is. I told you, I mentioned earlier that electrons and these other fundamental particles have a quantum mechanical property called spin. If you ever take a quantum mechanics class, do not think of quantum mechanical spin as the particle literally spinning. But in terms of the symmetries I want to talk to you about, you can think of this as just a ball spinning, a negatively charged ball spinning around in a circle. So you can think of it spinning left to right, like I've drawn you in this arrow here. The way we sort of denote a particle spinning from left to right, like I have here, is with something called the right hand rule. So the right hand rule is you take your right hand, not your left hand. You take your fingers, these four fingers here, and you curl them around the same way the ball is spinning. And when you curl your fingers around the same way the ball is spinning, you look which direction your thumb is pointing. And you realize your thumb is pointing up. So we can draw a vector, the spin vector, which I'm denoting here, which should have a little vector sign on the top of it that points up. And again, the ball is spinning around this way, my thumb's pointing up, so we say it's pointing up. If it was spinning around the other way, my thumb would be pointing down, and the spin vector would be pointing down. So again, we can think of electrons as negatively charged particles that are spinning, and the way I'm drawing it now, it's spinning, so we draw its vector up. So this is what we know about electrons. We know they're negatively charged, have a spin, and also a mass, but we don't have to worry about that part for now. And we know this is what's going on in an electron. Now, let's make an assumption that we don't know is true, but that might be true. So now we're going to assume that electrons have something called an electric dipole moment. So an electric dipole moment is just when there's more charge on one side of a system than the other. So if the charge in an electron really looked like this, where you take away some of the charge at the top and you put it on the bottom, then you have a system with an electric dipole moment. And the way you draw an electric dipole moment as a vector is you find the part with more negative charge, and then you find the part that's relatively positively charged, and you draw it as a vector from the part that's more negatively charged to the part that's more positively charged. So if we're assuming that electrons have this electric dipole moment, in this case, the electric dipole moment would also be pointing up. It's pointing parallel with the spin. And again, according to the standard model, according to the best measurements we've made so far, there is no electric dipole moment. This doesn't happen in electrons, but it might. It might just be a really small effect. And let's assume that it's there right now. So there's a spin parallel with the electric dipole moment. And the exciting thing about an electron or any other fundamental particle with that has spin and an electric dipole moment is that it violates time reversal symmetry. So here I've drawn you the same electron. There's negative charge smeared out throughout the whole thing, but we can ignore that. Just focus on the dipole moment. And again, the dipole moment is pointing up and the spin is pointing up because it's rotating from left to right like this, just like it was on the last slide. Now, if you take a video of a particle that's spinning from left to right, and then we play that video backwards, obviously it's going to be spinning in the other direction because we're watching the video backwards. We see that it's spinning the other way. But the dipole moment, you can really think of this as just taking a lump out of the top and putting it on the bottom, so you have more negative charge on the bottom. If there's a lump on the bottom when you watch the video this way, there will be a lump on the bottom when you play it backwards. So this dipole moment is going to be pointing the same direction. And because we have two physically different systems, one that we see happens forwards in time and one that we see happens backwards in time, we have this would be evidence of violation of time reversal symmetry because the electrons look fundamentally different going forwards in time than going backwards in time. So if we can find and measure this electric dipole moment of electrons, this would be proof that nature really does violate time reversal symmetry. And again, if we violate time reversal symmetry, we can get a universe where energy makes more matter than antimatter, and we can solve the problem that I talked to you about earlier in the talk. And that's what I've just said. So this is actually exactly what my experiment's looking for. Here at Colorado, we're looking to see if electrons have more charge on one side than the other. And we do that using a molecule called hafnium fluoride. And hafnium fluoride is a useful way to talk about it. If you have time to stick around, I can tell you more later on. And that's what we're doing here at Colorado. I also wanted to mention what I was doing at Amherst and Yale. We were looking to see if protons have more charge on one side than the other. It's a little more complicated because, like I said, protons are composite systems. They're made of up and down quarks. But if protons have more charge on one side than the other, protons also have a spin, they would be interesting for the same reason because that system would also violate time reversal symmetry. That experiment's called Centrex. The last four letters are T-Rex, hence the fun logo here, which is why really the whole thing I included it because that logo is fun. So I don't know if we want to break out into discussion groups or if we just want to ask questions first, if people want to head out relatively soon. But I have a discussion question about time reversal symmetry if people want to sit around and think about that for a bit.
Yeah, maybe we could take a second and let's thank our speaker. And then we can just say, if you're here for the talk and you have to go somewhere, feel free to go at any time. But Trevor, if you want, maybe you can just briefly talk about the answer to this discussion question and then keep going. And then if anybody needs to leave, feel free to leave.
Sure. So the answer to this question is basically that if you watch a real video of a mass oscillating, it's going to slow down. A mass on a spring, there's friction, there's air resistance, whatever. But it does not violate time reversal symmetry. So if you look more carefully, there'll be air particles that are, carrying energy and momentum away from this mass. And if you watch that video in reverse, what you'd really see is those air particles hitting it and speeding the system back up. So the same, and if you look at the physics of the collisions, all of that would happen the same way forwards as it does backwards in time. Friction's a bit more complicated, but it's basically the same story. If you look microscopically at what's going on with air resistance and friction, the universe works the same way forwards as it does backwards. So time reversal symmetry is not something that's normally violated. I know in my group, someone mentioned entropy. That would be a whole nother discussion about why that doesn't violate time reversal symmetry. But in general, the universe behaves the same way forwards as it does backwards. Okay, so I can just do like a super quick overview of the rest of my talk. how do I want to do this? All right, let's see. Basically, first I do have to explain what an electric field is, if anyone is unfamiliar with that. If you have a positive charge here and you have a negative charge here, this is just your system where these charges are fixed in place. You can think about how another positive charge would interact with these two systems. So if I put a positive charge right here, it'll obviously be repelled by this positive charge and attracted to this positive charge. So it'll experience a force away from this positive charge and near that positive charge. And if you combine those forces, you'll see that it ends up moving this way, like sort of tangent to the line that's drawn here. And what these lines are electric field lines, which basically are drawings of where a positive charge is going to be accelerated according to this equation here. Here's the system that is easy to think about. So if I have a positive charge here and this whole plate is filled with positive charges, this whole plate's filled with negative charges, it'll be accelerated from right to left. And then if I have a negative charge here, it'll go against the field lines. It'll go away from the negative charge and towards the positive charge. Those are positive and negative charges. What I'm interested in my experiment is an electric dipole moment. So having some positive charge on this side, some positive charge on this side. And you can think of this in an electric field. In an electric field, this orientation up here, the positive charge is going to want to go to the right. The negative charge is going to want to go to the left. And basically, because they're on the opposite sides that they want to be on, this is an unhappy configuration. The particles really want to be down here, where the positive charge is towards the side it wants to go. The negative charge is against the side it wants to go. And there's a really good analogy. Basically, this is, it's stable when this orientation is perfect, but if it's twisted just a little bit, it'll roll down the hill and want to get to this more stable configuration, because this is where the particles want to be. And basically, because this is an unstable configuration and this is a stable configuration, just like in classical mechanics, where we say this has more potential energy than this system down here that's more stable at the bottom of a hill, there's an energy difference between these two orientations. So the way my experiment works is we put electrons in a really big electric field and flip their orientation and see if we can measure any energy difference. And if we do that, then we found evidence of the electrons having an electric dipole moment. How we actually do that is we put electrons in the middle of a molecule, because molecules, certain kinds of molecules called polar molecules have positive charges super close to negative charges and can make way bigger electric fields than we ever possibly could in the lab. So we look at an electron in the middle of a molecule and we measure the energy difference of it oriented with the electric field versus against the electric field. And here at Colorado, we do that in a molecule called hafnium fluoride plus. Here's a picture of my lab. It's a mess, as you can see, but there are lasers, and all the way in the backs here where we actually do the experiment. So most of my job is just getting lasers to work, getting communications to lasers to work, getting communications between my computer and lasers and various electronics to all work at the same time. And there are over probably about 15 lasers, and getting all of them to be happy at the same time is hard because we only have 2 graduate students working on the experiment right now. Here's a picture of where we do the experiment. It's not an actual picture. It's a CAD drawing, a computer rendering of the trap. And basically, we have our molecules sitting in the middle here, where we can apply very precise electric and magnetic fields to hold the molecules in place, as well as access for all of our lasers to get in along all 3 axes you see here. So we can shoot the molecules with lasers. And that's actually the main part of my job, to shoot molecules with lasers. And we even have one laser that blows stuff up. It's a great time. Here's a picture of sort of what I've been doing from home when I have to work from home more recently, because we can only have so many people in the lab. This is an electric field rendering, a simulation of what's going on in a simpler system where we can understand it better. So we really need to understand the electric and magnetic fields really well. So that's a lot of what I've been doing from home lately. And here's a picture of the code we use. It's called LabVIEW. Doesn't involve any pesky writing and missing semicolons. It's all picture-based, and I think this is my favorite way to code. Nobody else likes it, but LabVIEW is fantastic. It's my favorite thing. And yeah, now I just want to point you to the people who are actually doing the work. Here's a picture of Eric Cornell's group. With some people here whose names I took out because they're no longer in the group or not working on this experiment. And then there are 4 of us who joined the experiment recently, along with 2 undergraduates. So, you know, we, Eric and June, try to keep the labs open to undergraduates if they want to join. And just in conclusion, what we do one more time is we're measuring the electric dipole moment of an electron. And we do that really carefully by using polar molecules, because polar molecules have the biggest electric field possible. So they lead to an energy shift we could possibly measure. If electrons have an electric dipole moment, they violate time reversal symmetry. They would look fundamentally different forwards and backwards in time. The reason that's interesting is because this needs to happen in order for the Big Bang and just big flashes of energy to make more matter than antimatter, which is clearly what we see in our universe. We see a universe full of matter with almost no antimatter. And that's the only way we can explain how we got here. So that's the goal of my research. Hopefully I explained it in a way you all could follow it and understand. And that is the end of my talk.
Thank you so much. Great job at condensing the last chunk of your talk. Thank you.
Thank you.
Yeah. Does anybody have, or do you have time for some questions still? We're not keeping you. Okay, great.
Yeah.
If anybody has any questions, you can raise your hand. And also, we've pasted a Tyler has pasted a feedback form in the comments. We appreciate your feedback. We use it every year to make the talks better. So it takes like literally 3 minutes. The link is there for you. Go click it and fill it out. Tell us how the talk was. Give any comments to the speaker that you'd like them to have if you thought they did really well. Hassan?
Yeah, I had a question concerning antimatter. So is it true that there's like naturally occurring antimatter and like, or is it like sort of like synthetically made in a lab? It just like it kind of like didn't make sense to me. That like matter should exist antimatter should exist in a universe in a matter universe, because wouldn't it just like immediately annihilate, or like
yes,
is there like
so a few things. The first is that antimatter is naturally occurring. It happened naturally after the Big Bang. Humans certainly didn't have anything to do with that. I think what you were more asking is antimatter in the universe now. No, as far as we can tell, there is no or incredibly little amounts of antimatter in the universe, because if there was antimatter, like in my room, for example, it would run into something made of matter and it would make an explosion, and the feed to this video would cut out. So no, there's no antimatter now. What we can do is what happens at CERN, the big research center in Switzerland, is they can, make really high energy conditions by having particles collide with each other. And from that flash of energy that they make, they actually see matter and antimatter appear. And at least one or two of their experiments are really carefully try to hold on to that antimatter for as long as possible and measure it in a lab. But yeah, those are very abnormal conditions that they have to work very hard to make. What happens is, like, after maybe a second or even less than a second, those antimatter particles are going to run into some matter and they'll make an explosion and disappear. So yeah, it's definitely sort of like a synthetic thing that doesn't really exist right now.
Okay, so like you're saying like it's basically like impossible to create like a pocket of space that's entirely devoid of matter, or like that's kind of like, are you saying like this kind of, well, yeah, I don't know, that was my question. Yeah.
I guess if you went out into outer space where there's very little matter and you somehow made a very big flash of energy, then matter and antimatter would form for that. And, since there's almost no matter in space for the antimatter to run into, except the stuff you just made, maybe some of that antimatter can fly off and exist on its own for a long time. Like, for example, maybe there are positrons floating around like deep in outer space that are just away from everything else. And that in principle could exist for a very long time. So there's no reason there can't be some antimatter out there. It's just that when we look out at the sky, the planets, the galaxies and stuff, everything we see is made of matter. If there were pockets of space made of antimatter, that would actually be something that we could detect, and we just don't see that. So.
Thank you.
How would we be able to detect said antimatter clusters?
Yeah, so this is actually something that we had to consider, or it was actually important to think about, because if, say, the Big Bang happened and it made just as much matter and antimatter, except all the matter went this way and all the antimatter went this way, or maybe that's not what happened. Maybe there are just pockets of space made of matter, pockets of space made of antimatter, and we happen to be living in one of the ones made of matter. basically what would happen is there would be domain walls. There would be these borders between these regions of space where matter and antimatter would collide. Matter and antimatter, if they collide, they make energy, they make light. And basically we would be able to detect that light because that light would come in at a particular frequency, and it would be, you know, huge, right? Because there would be these huge domain walls of matter and antimatter colliding that astronomers would be able to see. And basically there's a pretty unique signature that would come along with that, and they just haven't seen that anywhere, which is why we think the universe is made of matter everywhere. But yeah, that's a good question. I've heard that one asked by professional physicists at talks a few times.
Oliver?
I was wondering if an electron has a electric dipole moment. Does that mean it's not a fundamental particle anymore and that it's made up of like different quarks or something?
That's a good question. So no, we think the answer to that is no. Electrons, as far as we know, are actually a little bit more complicated than I've shown. They're really point particles. They don't take up, they're not extended in space at all. They really only exist at one point. So you can ask, well, how can they have more charge on one side than the other if they're really just point particles? And the answer is kind of complicated. It's that electrons the electric dipole moment would be generated by interactions between electrons and other particles in space. So basically, there's a theory called quantum field theory, which is sort of the basis of the standard model, which says that every particle, all 17 of the particles I've shown you, can pop in and out of space randomly. And the electrons would have some constant background interaction with these fluctuations, basically, of these particles, and that would lead to an effective, there being more charge on one side than the other. So the takeaway is electrons really are, as far as we know, fundamental particles. If there's more charge on one side than the other, it's because of interactions with other particles.
Okay, thank you.